Hello and welcome to this talk. This talk is called Computable Analysis and Verified Exact Real Computation in COC. My name is Holger and this is joint work with Michael Konechny and Florian Steinberg. Let me start this talk with a little bit of motivation. Our background is from the area of computable analysis. Computable analysis is an extension of classical computability and complexity theory to real numbers and other uncountable mathematical structures from analysis. Typical questions in this area are what kind of problems in analysis are computable, for example, by using the Turing machine model, and relating problems in analysis to classical complexity classes like P and NP. However, the computational model in computable analysis is realistic in the sense that it can in principle be implemented on a computer. As such, software allows exact manipulation of real numbers. It is sometimes known as exact real computation. Algorithms from computable analysis come with a mathematical proof of correctness by design. For even higher reliability, it is desirable to have formal versions of these proofs verified by a proof assistant. Florian, one of the co-authors of this work, is therefore developing a library for computable analysis in the COC proof assistant. In this work, we use this library, which is called Incone, to do verified exact real computation. The algorithms and definitions that we write can be extracted to executable Haskell code that we can use to do real number computations. Let me now talk a little bit about the computational model in computable, about some of the main definitions from computable analysis and how they are implemented in the Incone library. Computable analysis is an area of classical mathematics, and as such, we assume that the existence of abstract non-computational mathematical spaces, such as, for example, the real numbers. Computational content is then added to the structures in a second step by encoding elements from subsets by elements of Baire space. That is, by functions from natural numbers to natural numbers. Formally, a representation for some abstract space X is just a partial surjective function from the Baire space, that is, from the space of functions from natural numbers to the space X. We further call elements of Baire space that are mapped to some elements X, names for X, and call the pair of an abstract space and its representation a represented space. In the Incone library, represented spaces are defined similarly. However, instead of encoding everything explicitly by finite strings, we allow slightly more general encodings that make things more practical. So how is a representation defined in the Incone library? So a represented space in the Incone library consists of the following things. So the first thing is an abstract base type X. So this can be any type. This can be an arbitrary type in COC, and usually this type will have a definition that is in some sense not computational. So that will somehow rely on. So in COC that means it will somehow rely on some non-computational axioms. So the definition of this type uses some non-computational axioms. Then the second thing is we define a space of names, and now for the space of names, we allow names to be arbitrary functions from some space Q to some space A. And we call Q the questions and A answers. And the only requirement that we have on those types Q and A is that they are countable. So we have to provide proofs that they are countable. And then finally, a partial surjective function from the space of names to X, which we call representation. And the idea is that for elements of this abstract space X, we have those countable questions and answer types, and the name for such an element of this abstract space is just a function that we can ask questions of type Q, And that will give us, for such questions, will give us an answer of type A. And if we ask enough of the right questions, we will be able to approximate this X arbitrarily well. So this is how a represented space is defined in Incone. And let's look at some simple example. So the most basic example is probably the representation that encodes the real numbers, by rational approximations. So in this representation, the question and answers are both just rational numbers, and the name for a real number is defined as a function that gets some rational number epsilon. And if it gets an epsilon that is larger than 0, then it will return an epsilon approximation to X. So using this function, we can get arbitrary well approximations of the real number X. Okay. A useful thing about those represented spaces is that they allow to automatically generate more complicated representations from existing ones. In Incone, for example, if we are given represented spaces X and Y, we can automatically get definitions for standard representations for the following spaces. So one is, for example, for the product space, for the coproduct, for infinite sequence over some represented space, for the space of subsets, and for the space of continuous functions from X to Y. Okay, so representations now allow us to add computational meaning to functions between some abstract mathematical spaces X and Y. So how is this done? So for this, we use the notion of a realizer. So what is a realizer? So a realizer for some function from a space from abstract space X to Y is just a function on the naming spaces of X. So the space, so this is the space from questions to answers of the space of the represented space X, and this is the space from questions of functions from questions to answers from the represented space Y. And a realizer is now just a function that gets names for elements from this space X, and then has to return names for elements that correspond to f of X. And in computable analysis, the notion of a function is sometimes too restrictive, and we therefore also want to consider a less restrictive notion, namely that of a multivalued function, or multifunction for short. The idea behind the definition of a multivalued function is that for one input we allow several possible outputs. So formally, we can define a multivalued function just as a relation or a set-valued function, but in summer it makes more. So it kind of makes more sense to think of it as a kind of non-deterministic function, where for a given input there are several possible valid. So for one input there can be several possible return values, and we do not really know which return value we get. So all of them are valid return values, and we can just get one of them, and this will be a correct answer. This is reflected in the notion of how a realizer is defined for multivalued functions. The notion of a realizer can be extended to multivalued functions by saying that a realizer for a multivalued function is just a function that maps names for elements from this space X to a name for any valid return value of f of X. So far, we have only seen the notion of representation applied to the real numbers, but so this notion is much more general. For example, we can also use representations to define computation over non-discrete finite spaces. One such space that has many useful applications in the theory of computation is Sierpiński space. And Sierpiński space is just a topological space which has only two elements that we call top and bottom. And there's only one set that is open but not closed, namely the set only containing top. So we can define a representation of this space that induces the same topology by using the following definition. So the standard representation that we use for Sierpiński space is we let the questions are just the natural numbers, and the answers are the booleans, so just true or false, and the name for an element of Sierpiński space is a function from the natural numbers to the booleans that is defined as, and the representation is defined as follows. Such a function is a name for top if and only if there exists a natural number that so there is one natural number such that phi of n is equal to true, and the only name for bottom is the function that for all natural numbers always only returns false. And so a possible interpretation of this space is that it models terminating and non-terminating computation. So if a computation terminates, then there's some finite time. So there's some finite time m for which the computation stops. So then we can return true. So we know that it stopped. But if it doesn't stop, if the computation doesn't stop, then we will never know, and we will always return false. Another useful finite space is the space of Kleeneans three-valued logic. So this is kind of an extension of the booleans. So we have, like the booleans, we have 0 and 1, which correspond to false and true, and we have a third element bottom that kind of stands for undefinedness. And this can be turned into a represented space by using the following representation. So again, the questions are just the natural numbers, and as answers we use 0, 1, and the third element none. And we define the representation as follows. So a name is a function from the natural numbers to 0, 1, or none, and we say it's a name for 0 if the first element that is different from none that this function returns is 0. We say it's a name for 1 if the first element that it returns is 1. And we say it's a name for bottom if this function only returns none. So this definition is kind of useful because we can often use it to kind of delay the Boolean decisions to some later point in time and to extend partial Boolean decisions to total functions, because this additional natural number parameter m here, so the way the representation is defined here allows us to kind of for some time say nothing, so return none, and just delay the decision to some time and then say either true or false, or if there's no decision, so if this would not terminate at all, just always return none. So this can often be used to extend partial Boolean functions to total functions so partial Boolean functions can often be extended to total functions on the Kleeneans. And one important such example is that we can use the Kleeneans to define a total computable real comparison, which is defined as follows. So if x is if x is not equal to y, then it just returns the Boolean. It is just defined as the Boolean value, and if x is equal to y, then it is defined as the bottom, as the bottom element. And if we, for example, it can be seen that, for example, if we use the representation by rational approximations, the rational representation for real numbers that we have seen on one of the previous slides, then this can be this function can be a realizer for this function, a computable realizer for this function can be easily defined. So if we now want to use the Incone library to write some exact real arithmetic algorithms, the typical steps, what we have to do is the first thing. So the first thing we do is we want to give an abstract mathematical description of the problem as a multifunction. For example, and so this is just an abstract mathematical description with no computational content. So this will, for example, use the axiomatic real numbers. So there's an axiomatic definition of the real numbers defined in Coq's standard library that we can, for example, use for this. And then we define a representation for the, or we choose a representation for the real number. So of course we can, so of course we don't have to do this every time. We don't have to do this every time, but we can just define some representations of real numbers and then reuse them all the time. So the second step is just choosing some representation for the real numbers. And then what we have to do is we have to add some computational content by defining a computable function on the naming space, so on the on the naming space of this representation, so on the space of so defining a computable function where the input is a function from questions to answers of this representation, and the output is also a function from questions to answers in this representation. And well, so I say computable here, but what this means in practice, because so Coq's internal logic is already constructive. So instead of computable here, it often it usually what we usually do is just we define a function. We define a function in Coq that doesn't rely on any external axioms or on any non-computational axioms. And then since the logic of Coq is constructive, this function will already be computable and we can execute it in Coq. So this is what we usually do. So and then the last step is proving the correctness of this. So and this means that we prove that this function that we defined here is actually a realizer for the multifunction that we defined in the first step. So in this sense, how things are done in Incone is somehow similar to classical program verification, in the sense that we have a constructive definition, so we have a computable definition of a program, and then we have a formal specification in terms of the multifunction that this program is supposed to be a realizer of. So we have an abstract specification, and then finally we prove that this program actually fulfills the specification, so the correctness proof, which also can use classical mathematical logic, and so finally give a correctness proof that the specification fulfills the specification, that this program fulfills the specification. Or in our setting, this means the correctness proof is proving that proving that a function we defined is actually a realizer of the abstract multifunction that we defined. However, in this way, so whenever we want to define some real function, we have to give a very low-level implementation that heavily depends on the underlying representation. So we therefore want to do things a little bit more generally, and so this idea is kind of inspired by more practical frameworks of exact real computation that, for example, are implemented in C++ or Haskell, so non-verified implementations of exact real computation. Because in such frameworks, they are usually, so what they do, they usually provide some basic operations on real numbers, like arithmetic operations and so on, that can be used, that can be combined to define more complicated programs. And we wanted to define something similar in Coq, built on the Incone library. So we call this a structure computable reals, and this structure does something similar. Namely, it provides some basic operations on the real numbers. So so I mean, what I mean by this is defining, so instantiating this structure means to provide realizers of those basic operations, and then we can use those. Then we can use those basic operations in more high-level programs. So can combine those basic operations and then do some more high-level proofs where we use those basic operations and combine them to more complicated functions and write the proofs independently of the underlying representation. So it also allows us to easily switch, easily exchange different representations and so on. So what are the basic operations that we use? So the following operations turned out to be useful. So the first thing is we want to have realizers for basic arithmetic operations. So addition, subtraction, multiplication, and division. Then an implementation of the efficient limit. So the efficient limit is a function that takes a sequence of real numbers and returns a real number. That gets a sequence of real numbers and then returns a real number, and this real number. So the return value of the sequence is if this sequence gets of this function is if this function gets as input a sequence of real numbers that is efficiently Cauchy. So that means it efficiently converges to some real number x. So that means the i's term of this sequence. The i's term of the sequence is at most 2 to the minus I far away from its limit. Then we will return the limit of the sequence. We also want to provide a realizer for the Kleenean comparison function that we have seen on the one of the previous slides. And also we want to have some operations for easily doing input and output of real numbers. So we want to implement a function that we can give to integers m and e, and then map to the dyadic rational number m to the 2 to the minus e. And we want to be able to output rational approximations. So we want to have a realizer for the multifunction that gets a real number x and the rational and an error bound epsilon, and returns some rational approximation of x with error at most epsilon. So in our current work, we already instantiated this computable real structure with 2 different representations. The first one is the simple rational representation that uses rational approximations that we have seen as an example on one of the previous slides. And there's, so working with rational numbers is usually not very efficient. And therefore we also implemented an alternative representation that is inspired by efficient frameworks by efficient non-verified frameworks of exact real computation. And this is based on interval arithmetic. So instead of using rational approximations, we use sequences of intervals with dyadic endpoints. So we use sequences of intervals with dyadic endpoints to approximate real numbers arbitrarily well. So the formal definition of the representation is that the questions are the natural numbers, which just means we have sequences, and the outputs are of some interval type. So intervals with the interval type of intervals with dyadic endpoints. And then we say such a sequence of intervals is a name for some real number x. If x is contained in each of those intervals, and if the intervals, if we increase the precision parameter n, then the intervals will get arbitrarily small. And to implement this in Coq, we didn't have to start from scratch because there's already a huge library for doing interval arithmetic in Coq, which is called the Coq interval library. And this library provides already many basic operations on intervals, such as, for example, addition and multiplication and so on, that we can use to write the realizers for operations, for the basic operations for this representation. In the paper, we give a larger example of how those operations can be used. Namely, we give the example of computing the square root using the well-known Heron's method. But for time reasons, let me here just introduce a simpler example. And the motivation for this example is that comparison of real numbers in exact real computation is often problematic because Boolean comparison can only be implemented as a partial function because it is undecidable if 2 real numbers are equal. And the Kleenean comparison doesn't really resolve this. Because in the Kleenean comparison, if 2 numbers are equal, we return bottom, and the name for bottom does not really give any information. So in exact computation, therefore often another form of comparison is used, a multivalued version of comparison, which is called soft comparison, and it is defined as follows. So it is a multifunction that takes the two real numbers that should be compared, and additionally a natural number parameter, and maps to the booleans. And so true is a valid return value for this multifunction if and only if x is less than y, and false is a valid return value for this multifunction if and only if y is less than x plus 2 to the minus n. So this will always return at least one Boolean value, but there's a small interval of size 2 to the minus n where both true and false are valid return values of this function. And we can define this form of comparison by using our basic operations. Namely, this can be defined from the Kleenean comparison, because if we replace those tests here by the Kleenean comparison tests, then we know since always at least one of them will be true. So if we search in the name, if we search in parallel in both, if we do the Kleenean comparison and then search in parallel in the names, the search will always terminate and find out which one of those is true. So we can always return a value. Okay, so let me end this talk with a small conclusion and some future work. So what we have seen is that the Incone library can be used to implement real number computation in COC and the proofs in the style of computable analysis. And we have just given a simple implementation, but the simple implementation that is based on interval arithmetic, we tried it with a few examples and have seen that it's already quite efficient, so comparable to non-verified implementations of exact real computation. And in the future, we want to do a few things. So for example, we want to look at not just at operations on real numbers, but on, for example, we have started on looking at more complicated spaces. So for example, what we have looked at is the space of analytic functions. And then an interesting operation to do there would be something like ODE solving. So this is the end. Thank you very much for listening.